In this lecture, we are going to look at a case study of how to use the unit processes that we discussed throughout the lecture and use it for some application. In this case, we are going to exploit CMOS compatible fabrication processes for doing photonics, in particular silicon photonics. So here we are going to look at CMOS process flows and key technology steps that is required to realize a silicon photonics application. So what you see here is a cross-section cartoon of what one would like to have. For instance, you take a silicon on insulator, it's called SOI, silicon on insulator wafer, where we make active devices in one layer. So you can see just different etch depths, right, and realizing various devices. And also we have metals, right, to make heaters, and sometimes different type of material to bring in and realize various functionalities. So what we are essentially trying to do here is exploit silicon as a platform and then make various devices just by etching or doping or adding new material, right, in addition to silicon, and make various metallization contacts in order to realize the desired functionality that you want. So what you see here is a cross-section cartoon, so which is pretty easy to make when you are using PowerPoint or any other CAD tool. But then let's look at how we can realize this on a wafer. So the primary reason for using silicon microelectronic process, right, is its success in standardization. So all the microelectronic process that we see, it's all standardized. So what I mean by standardization is they're all modularized. So that means you have to put various Lego blocks or various process modules in order to realize functionalities that you desire. So in some cases you might have a really good idea, but if we cannot standardize the process, then you won't be able to realize whatever great ideas that we have. So it is rather sad that we cannot realize some of these great ideas. So that is the nature of life cycle when you look at large volume fabrication. In a standard integrated fabrication platform, what we do is we use standard platform, right? So standard modules that can be used, right? So the standard processes should be within the tuning range, right? So the requirement that you have in order to realize some device should be within the range of that particular process that it can deliver. So if the line width variation that a process, a standard module gives is about 5%, and if your requirement is 0.5%, then it is impossible to realize whatever design that you have. So it should be in that workable range of that standard process. So everything should be modularized. So unless you make modules out of your process flow, then you won't have any consistency. So we have to make sure that there is a module so that there are no inconsistencies in realizing that process. Let's look at a simple modular approach of how we can do a simple process flow. So I call this as a wafer cleaning module, right? So that cleaning module would include organic clean, inorganic clean, and metal clean. All this is encompassed in one cleaning module. So we call this as a cleaning module. And then in the next module is a waveguide module. I mean, this is a certain type of device and I have made a module out of this. So when I say this is a waveguide module, that means there is lithography step, etch step, and then removal of the photoresist, and then a clean step. All of this is encompassed into a module. So after this waveguide module, there is a coupler module. This is again another device module. So that again includes lithography, etching, photoresist removal, and cleaning step. So what I can do is I can take this particular module and then place it wherever I want based on the requirement from the designer side. Similarly, this wafer cleaning module, I can make this cleaning module in between processes also, right? In order to make sure my transition between one module to the another module is all contamination or cross contamination free. And then we have this planarization. We have discussed a lot about chemical mechanical polishing. So polishing is again a module. So in this case, first you start with deposition. We have to do polishing in order to make the wafer flat, and then wafer cleaning as well. So everything is encompassed. So a discrete module is a collection of a complete unit steps in itself. And then if you need some sort of thermo-optic tuner or some metal heaters, then you start with metal deposition and lithography of metal, and then you etch metal and then remove the photoresist and then clean it. So this module can be used by anyone who wants to make a thermo-optic tuner or a metal heater. So when you create modules, you make sure that it is reusable, right? And then you can adapt each of these modules for a desired application. So let's look at each of this process and what are all the requirement within this each module. So in order to visualize, normally a process engineer would make a flow cartoon like this. So you start with a silicon on insulated wafer. The first thing that you do is you coat the layer with bottom anti-reflective coating, and then you bake the bottom anti-reflective coating, and then you do a resist coating, in this case photoresist coating, and then after that you do a soft bake, right? This is pre-exposure bake. And then you go for exposure, and this is the step where we illuminate required structure, right, the required design onto the photoresist. And after that we do post-exposure bake, and after the baking is done you do a development. So when you are doing the development, the region that are unexposed will be removed, or the exposed part will be removed based on the tone of the resist, whether it is negative resist or positive resist. And once the development is done, we do ICP etching. So inductively coupled plasma reactive ion etching is what you do to remove the silicon layer that is exposed, and then we remove the photoresist to end up with a simple silicon wire, right? So this gives us a very natural way of visualizing how the process would look like. If there are any issues that you encounter while making this process flow, then you will go back and look at the developed process flow and then address those issues. So always it is better to visualize whatever process flow that we have before starting any process. So once the process flow is done, then we start doing individual process modules. Let's look at first wafer cleaning. Why wafer cleaning is important? In particular to photonic application, the contaminants results in absorption. That means light absorption and scattering of light. So we need to make sure the wafer is clean. So that means clean from any particle contamination, metal contamination, or any ion contamination, including organic contaminants as well. So we want to remove all these contaminants from the surface in order to make sure that our starting substrate is clean. We can either do wet cleaning or dry cleaning. So when we say wet cleaning, this involves using of solvent, HF, or RCA clean, Piranha clean, or ozonized clean as well. So all of these are done using wet chemicals. So when we use wet chemicals, we call it as wet clean. And then in dry clean, we can use plasma directly or any kind of gases that can etch away this substrate, right? So these are all something that we have already seen in our unit process. This is just to recap on that. So the mechanism that we use is primarily oxidize and remove the contaminants, or oxidize the underlying substrate and then remove the underlying substrate so that you can lift off, and then create a very thin layer of native oxide so that your substrate is protected from further attack from any kind of contaminant. So once it is done, we can also look at the kind of contaminants that you could have. For instance, here this is very clean substrate. We have went through all the clean, but then you can see trace amounts of metal, right? If you expose your substrate to any kind of beakers or any vessels that you use in order to clean this material, then the contamination on that particular glassware will come and sit on this substrate, and you're going to find it difficult to remove it. And this can be very specific to the position on the wafer or position on the structure itself. For instance, this is a clean step after dry etching. You can see at various positions, right? At position B, there is no contaminants whatsoever, but then as you move down, right, at position E here, you see an increased metal contamination here. So one need to be sure about the distribution of contamination, not just on the wafer but also on the structure that one prepares. So once it is clean, the next step is lithography. So we can do lithography in multiple ways, and this is something that we have captured in the earlier lectures. So primarily we are looking at optical lithography or electron beam lithography when it comes to academic research or industrial scale process. So primarily industrial scale processes use optical litho. In this case, we are going to use optical projection litho for patterning the structures. So the evolution here is shown starting from 0.18 micron to 0.13 micron, and the present day 45 nanometer or 22 nanometer node technology. So the lithography technology that we use is 248, 193 and 193 immersion. So what is the advantage and disadvantage in using this? So 0.18 nanometer, 0.18 micron technology gives you a pretty good patterning, but then what you see here is the effect of proximity. You can see here the difference between the bulk holes and the edge holes, right? So this is about 40 nanometer. So there is a 40 nanometer difference between the holes on the edges, right, and holes at the bulk, right? And if you go to the next generation technology, in this case 193 nanometer lithography technology that is used for 130 nanometer node, you can already see there is a reduction in the variation that you see, right? So this is already reduced to about 5 nanometers, right? So there is an order of magnitude improvement that we see when you go from one technology node to other technology node. So this brings me to the technology selection itself. So what is the requirement? So what is the final structure should look like? What is the specification on the device, right? Now the overall device and within device as well. So in this case, this is an overall device where there is a within device variation, and this within device variation is addressed by going to advanced technology node. And then if you look at 45 nanometer and 20 and below nanometer technology node, you are able to pattern really small features. So this opens up new avenues for integration and advanced devices. So it is not just about resolution, it is all about uniformity and adaptability of this technology to come up with new innovative ideas as well. So the patterning is evolving at the same time. What is your requirement and how do we choose also plays an important role. And once we pattern the device, next thing is to etch, in particular dry etch this device. And this is something very important. So I would like to highlight the chemistry that we use is a very important factor. So here we use oxygen and HBr chemistry in order to make the silicon etch. So what you see is silicon. When you change the silicon, silicon etch chemistry here by reducing the oxygen flow, you can see here you go from a positive slope to a negative slope, right? So that is what you see. So as you reduce your oxygen content, you can make your sidewalls pretty steep. So this is how you optimize the chemistries. So this chemistry change not only affects the profile, the physical profile, it also affects the performance of the device as well. So here I show you two different kind of etch process that is used. One is a vertical sidewall and one is a sloped sidewall. So what you see is the propagation loss, right? So alpha is loss here. You can see a vertical sidewall gives you a 3 dB per centimeter loss, that is about 50% loss, but when you look at the sloped sidewall, the loss is less. The reason for that is when you have a sloped sidewall, we have studied in our unit process lecture that the sidewall is coated with a polymer. That means the sidewall is protected. But when we look at the vertical sidewall, the sidewall is not protected that much. So you will see attack from the plasma creating scattering loss. So at the same time, we can also look at the bending loss. So when there is a bending, when you use a vertical sidewall, the bending loss is pretty low, right? So the bending loss reduces compared to a sloped sidewall geometry to a vertical sidewall geometry. So what I am trying to say here is it's not just the profile that you see, but the profile can also affect the performance. So this may be a device that is of electrical nature or optical nature or electromechanical in nature, but the profiles will have a certain influence on the performance as well. The next thing is about variability. So once we have etched all these structures, let's look at how the variability is going to affect. So this is something that I would like to elaborate on, where your variability, either width or height variability, will directly affect the performance. In this case, we are looking at the resonance of a certain device, which depends on the density of this material and the optical path length L, right? So there is a length of this material or length of this device and this density of this device. So you will have a change in the response based on change in this, right? So what you see here is this line width variation and thickness variation as a function of waveguide width or waveguide height, right? So this is H and this is W, right? So when there is a variation, you can see here dN, dW and dN, dH, right? So this variation, right, when you are close to the operating point is pretty high, right? So the slope is very high here. So you want to make sure that your operating point is chosen in such a way that your variation is taken care. So for instance, in this case, you want the slope to be rather flat, right? You want to operate in this region as opposed to this region. So when the slope is very sharp, nanometer variation could result in a nanometer variation in your performance. So you want to avoid that. So all the processes should be controlled in order to get uniform distribution. So the variation can be of multiple nature, right? So we could have spatial variation, or you could have spatial and temporal variation. So this depends on whether you are processing a single die, a small piece of wafer, or you are doing multiple wafers and multiple wafers in batches. So depending on your scale of manufacturing or fabrication, your variation will also scale. So the variation can come from any process that we are using. So one should be aware of each and every step will add non-uniformity and variability, and we should try to reduce the number of process steps and collate the process step in order to make efficient process flow that will reduce your non-uniformity. So your non-uniformity may or may not come from the processing that you are doing. It may come from the substrate itself. So what I am showing you here, the thickness variation of silicon in a silicon on insulator substrate. So what you see here is the variation of this top silicon layer within different wafer and within a wafer. So you can see here within a wafer you can have about 4 nanometer variation, but between wafer to wafer the variation could be much smaller. So that is what we see here. There is a within wafer variation of 3%. However, wafer to wafer variation is about 2%. So it is less than within wafer variation. So when you are processing multiple wafers and multiple batches, the variation can be not just coming from your process, it can be from your starting wafer itself. So this is something one should be aware of. So your lithography can also bring in non-uniformity. This is something that we already discussed, right? So the position of your device, right, within your chip can also play a role, because when there is a non-uniformity in the dosage that we use, right, that is as illuminated across your die, you will have various line widths, right? So when you take this variation in those, you are going to have variation in line width as well. So the placement of device is also very important. So make sure that you are aware of the placement related non-uniformity while you are taking into account the global uniformity of your circuitry. And this also helps when you go from different type of patterning platform. So here you are looking at 130 nanometer node compared with 28 nanometer node platform. So when you look at the patterning accuracy here, the spread, right? So 1 sigma, the standard deviation, is 2.5 nanometer in silicon. However, when you go for a high-end technology, this becomes 1.4 nanometer. It's almost half. So this reduction comes from superiority in the patterning technology itself. So when you are going from one process technology to another processing technology, then you improve the non-uniformity as well. So it is important to modularize all the processes that you do so that we can get maximum out of each module. So another important thing is variability as a function of space, right? So this is a spatial variation. What you see here is a single device, and it is surrounded by some dummy features, and there is a distance variation that we are giving here between the active device and a dummy device. You can see here this is with no dummy. The device resonance is somewhere here, right? So when you start putting closer and closer this dummy device, the features, the response is affected by this dummy structures, and then when the distance moves away, then it recovers back to the dummy level, right? So if you look at the distance between the dummy and the active device, this can be as large as 30-40 micron. So even devices that are 40 micron apart, they can influence each other. So this influence is coming from the wafer scale plasma processes that we are doing. So if you remember the plasma process, when the radicals come onto the wafer surface, the radicals can migrate based on the energy and substrate temperature and everything. So based on this, it can diffuse on the surface, and this diffusion length can affect your neighboring device uniformity as well. So just to give you an example, there are 4 different type of devices, and based on the density, so what you see is a density increase, and also your performance or your device response also correlates with the density of your device around the particular functionality that you have, right? So it's not the device that you're interested in, but also the environment. We should make sure you control the environment as well, so that there is a uniformity across the wafer or across your designed chip, that these variations are taken care. The next important thing is to cladding, right? So you put a coating on top of your device in order to protect the device. So normally silicon dioxide is used as a typical cladding or coating material, and this is used in multiple places, right? Active area isolation, it is used in gate dielectric, gap filling, and intermetallic filling. All these places we use silicon dioxide. So we can also use nitride carbides, for example, and we can also use silicon dioxide for various other application. So here we use silicon dioxide because it goes very well with silicon, so that you have good contrast, optical contrast between these two materials. When I say optical contrast, the density, the refractive index of silicon is 3.45. This is for silicon, and silicon dioxide is 1.45, right? So this delta N that we see here is something very important in photonics. So the choice of silicon dioxide comes in because it is non-absorbing. At the same time, the refractive index is pretty low. So there are multiple ways to deposit silicon dioxide. One is a PVD method. We can use evaporation or sputtering, or we can use a CVD technique, either atmospheric pressure CVD, low pressure CVD, or plasma enhanced CVD. So you can use any of this, and the implications are the precursors gases that you are going to use, and also the temperature of processing as well. So if you already have metal underneath, so you cannot use LPCVD, so you rely on PECVD or HDP process. So the deposition process, as we have already seen, can be conformal, right? Or it may not be conformal. So there is a implication of conformality on what kind of filling that you are going to get. So if it is conformal, the thickness is going to be uniform and you will not have much problem. But when you don't have conformal filling, you start creating these sort of overgrowth at the edges, and then you will close this, and that is what you will see here, right? So this is a LPCVD process, which is a conformal process, and you will not see any gap between these two silicon. So this is silicon and this is silicon dioxide. However, in a plasma process, you see here there is a gap. There is an air gap formed because the growth at the two end is closing, and then it creates a gap here. However, high density plasma oxide process will not create this, right? So the choice of deposition process is also very important. It's not just choosing any kind of material, but also what kind of process that one need to choose in order to realize a certain kind of device geometry that you have. It is not just the material, but also the composition of material. For instance, what you see here is a FTIR spectrum of a silicon dioxide material deposited with 3 different techniques. One is high density plasma CVD, plasma enhanced CVD, and TIOS based or LPCVD process, right? Since we use, though LPCVD process happens at higher temperature, right? So as deposited material, you see here really flat line, and what you are trying to look at is the absorption here, right? So this corresponds to water absorption, and when you see as deposited film, right, you see a slight peak coming here. This is coming from water that is present in TIOS material, right? Unlike the other materials, you don't have any water absorption at all. So even when you anneal it, right, so you have as deposited film here, and then even when you anneal it at high temperature, there is still some water vapor present there. So the water vapors are not still present when you anneal it. So post anneal, when you are going to cool it down, so water can diffuse in, and or rather the humidity can diffuse in, and then it will occupy the space that is available inside this oxide material deposited with LPCVD. So it is not just any technique. You should also be careful about the precursors that you are using, right? Though LPCVD happens at high temperature and we are also annealing at high temperature, but at the end the TIOS as a material is not good for some of the application because of water absorption. And the next thing is planarization. Once you deposited the film, you will see here this is something that we saw earlier, where if you don't do CMP or chemical mechanical polishing to planarize the layer, you will see all these kind of unwanted thickness variation and reliability issues. So you want everything to be flat and planar, right? So before CMP, right, this is as deposited. You can see here the topography. When you deposit, this is a conformal deposition, but then post CMP, it's rather a flat line, right? This is what you want, and it is not just flat, the surface roughness is also pretty good. So as deposited films might have a starting roughness of 0.7 nanometer RMS, but after polishing, this is 0.12 nanometer RMS. This is atomically smooth. So it is not just getting a flat wafer, it is also about creating smooth surfaces as well. So finally, metallization. So once you have this flat oxide, So we will follow lithography and etching step in order to make these trenches, and these trenches could be filled with metal deposition that we saw earlier, and then you do the CMP, right? So when you repeat this process, you can build complex structures as we saw earlier that should result in desired cross section that you want. So with this we come to end of this lecture, where we have seen that CMOS technology offers a lot of integration opportunities. The main reason for this is you create modules out of each unit process, and you make sure these modules can be used wherever you want, right, and arrange it the way that you want in order to realize the cross section that you want. And in order to get these modules right, one should understand the unit process so that you can utilize the technology effectively. So some of the processes may be limiting, right? So that could be the limit of what you can get out of this CMOS technology. You may add additional more non-CMOS like processes in order to achieve whatever is desired, but you should always try to standardize any modules that you would like to pursue. And as I mentioned earlier, if you want to make any commercial success, the process should be standardized and it should be compatible with the process technology. What I mean by process technology is the integration. So we should be able to stack all these standardized modules in order to realize the end goal. So as I mentioned, understanding is crucial here. We should understand the unit process, and we should understand what each modules will deliver. So once we get all those understanding done, we can make better device and circuit designs and realize those better. So with this, I would like to thank you all for participating in this lecture. I hope you got a feel for how to go about in making any kind of process flow from the unit process that we have, and make sure those unit processes can be put together in order to make a module, and these modules are compatible so that you can arrange the module the way you want and then realize a device or a cross section that you need. So the power of standardization should be followed, and before that, make sure that you understand the unit process and the module technology compatibility so that you can deliver a maximum out of the process.